In today's video, we'll discuss how to manually calculate game flipper latency on the AtGames Legends 4KP using a high-speed camera and a video editor, as well as demonstrate an internal measurement device for doing the same. I want to make you aware, as of June 2024, I began working directly for AtGames as an independent contractor. That said, I'm Jon, and welcome to Wagner's Tech Talk. Before we continue, it's important to understand what exactly is game latency and how is it measured. Game latency, also referred to as lag, is the delay between an action, such as the press of a flipper button and the amount of time elapsed when a corresponding measurable output results. 1 second is equal to 1000 milliseconds, or ms. Flipper latency is determined by measuring the time elapsed from the point in which the flipper button is pressed from the time the flipper begins to move on screen. A common method of calculating this latency is using a video editor to record the live action and measure both events. While measuring in milliseconds is ideal for measured accuracy, converting milliseconds to frames is easier to understand and a more accurate representation of the delay from a player's perspective. For example, the Legends 4KP playfield operates at 60 Hz. That is, in 1 second the display refreshes 60 times. Therefore, each frame represents 1/60th of a second. To calculate the duration of each frame, we'll use this formula, which equates to 16.67 milliseconds per frame. Therefore, if we measured 100 milliseconds latency, the number of frames elapsed would be 6 frames, 100 divided by 16.67. This approach provides a precise conversion from the time in milliseconds to the number of frames on a 60 FPS display. In order to calculate the latency accurately, we'll need a high-speed camera such as the GoPro Hero 10 shown here. The camera supports 240 FPS video capture, which will provide the accuracy necessary for our calculations. A cell phone can also be used, however, not all support 240 FPS. Some that do don't consistently output at 240 FPS. I'll show you how to verify that in a few moments. Moreover, make sure whatever camera you use is set for 240 FPS recording. You will also need a tripod and a camera mount. This camera mount will attach to the GoPro and screw in to a standard tripod mount. In this video, we'll focus on flipper latency. However, audio latency is something else you may want to capture. Audio latency is more difficult to analyze during frame-by-frame analysis. The reason for this is you can't be 100% sure what audio you're measuring. It could be audio from the solenoid, the flipper, or it could be background music. For this reason, we will focus only on flipper latency. But audio latency is also discussed in the written guide for reference if you want to check it out. That said, it's a good idea to make sure all audio levels are being captured as well. Move up to Settings and select Haptic Feedback. Move down to solenoid firing and enable this option if not already enabled. Then adjust the volume level on the machine to 70%. This way, if you decide you want to determine audio latency, the footage you record will have everything needed. Now load up a table and start the game. Position your camera pointed down onto the playfield. Make sure you have good lighting and can clearly see the on-screen flipper as well as the flipper button. Press record on your camera and record 10 to 30 quick flipper presses. After you've captured the flipper video presses, copy the footage to your computer. You'll then need a video editor. One that has been used by one of our development teams is called the Olive Video Editor, which can handle 240 FPS video. From the guide or the link below, visit the website and click Try Olive. Select the download for your operating system. I'll select the 64-bit installer. Then unzip the archive and follow the installation steps. After installation, launch the Olive application. Locate the video that you captured from the Legends 4K machine. Right-click on the file and click Properties. Click on the Details tab and verify that the frame rate is 240 FPS. While it's showing just slightly under 240 FPS in this instance, it's close enough. From here, simply drag your footage into the project, drag the footage onto the timeline, and when you see this prompt, click the button to automatically detect parameters from footage. From the menu, select View, and make sure the timeline is set for milliseconds. You can use the bottom scroll bar to locate the portion of the video where your flipper presses began. Right-click in the sequence viewer to zoom in closer and get a good look at the flipper button as well as the virtual on-screen flipper, and resize the window for optimal viewing. To begin our analysis, we'll skip to the part of the video where a button press begins. For more precise advancing through the video, the forward and back button can be used. Locate the point in the video where the button is pressed. Then click on the timeline sequence and press Ctrl-C in Windows to copy the starting location to the clipboard. In this case, I'll use Excel to paste the Start Flipper Press. On the sheet, once the flipper begins to move, we'll add the end sequence, which will give us our first flipper sample. We'll repeat for a total of 3 samples, then get an average of all 3 and calculate the number of frames on a 60 Hz display as we discussed earlier. And of course, the table we're measuring. I'll provide a download link to the spreadsheet in the description below should you want to repeat this test for yourself. Next, we need to locate the point in which the virtual on-screen flipper begins to move. We want to record the very first sign of flipper movement. To make it easier to see in this video, I'll expand the section in the upper left. Again, we'll copy the timeline sequence, which is in milliseconds, copy it to the clipboard, and paste it into our spreadsheet. Now we have our first sample demonstrating a latency of 54 milliseconds, and we can add that to our first sample. I'll now speed through the collection of our remaining 2 samples using the same exact methodology that we just discussed, as it's more of the same. Now we have our final sample of 66 milliseconds. The average of all 3 measurements is 60 milliseconds, and the number of frames on a 60 Hz display is 4. We've now calculated the flipper latency for the Dinosaur Dynasty table. Using frames for describing that latency is a much easier methodology than milliseconds to understand, however, both are important metrics. In a future video, and on the written guide, we'll take a look at measurements for several tables. Keep an eye on the guide, linked below, for updates. Now, imagine the amount of time needed to collect 10 to 30 samples as you've seen here, then repeat that for nearly 200 available tables. An idea was discussed with PK to allow us to more accurately measure latency by directly connecting to the flipper button and automating flipper detection. PK loved the idea of working smarter, and in this segment, we'll provide a discussion of our internal methodology for more precise game latency testing. The first step in automating the latency measurements is to build a simple board that allows immediate detection when the flipper button is pressed. If you try something like this yourself, you're doing so at your own risk. Here we have a screw terminal, a resistor, a diode, and an LED connected to 2 pins that will connect to the GPIO pins on the Raspberry Pi 5. To make sure I used an appropriate resistor, I connected a 9-volt battery to the board to make sure the LED would light up. It's a little hard to see with the workbench lights on, but the LED is a solid green. I'll just quickly double check that the voltage coming out is close to 9 volts. This happens to be a very old battery I'm using for testing, but it checks out fine. Now I can clip the excess wires off the board to prevent shorting anything out. And I've routed 2 wires into the cabinet for positive, or red, and negative, black, into and out of the Legends 4KP cabinet. Here I'm just screwing those two wires into the terminals on the solenoid board. Then reattach the connector to the solenoid board. I'll reinstall the control panel, strip and connect the two wires to the screw terminals on the custom board, and power on the machine. Now I'll do a quick check of the voltage coming from the Legends 4KP to make sure I don't damage the Raspberry Pi 5 GPIO chip. The voltage the Pi can handle is around 3.3 volts, and we're at a safe level at around 2.7 volts. Now we have everything mounted to this handy new stand that includes the ability to also mount a display. I can see immediately what the Pi is seeing. Here, the Pi and custom PCB is mounted to the arm, and when I press and hold the flipper button, the green LED on the custom PCB turns off. I can then program the Pi to detect exactly when this event occurs and record the time. In addition, we have a high-speed camera that can handle up to 260 FPS recording connected to the USB 3 port on the Raspberry Pi 5. This camera will provide the visual feedback to the automated latency tester, or ALT, as I like to call it. I've not had time to design a fancy 3D printed camera mount at this point, so electrical tape will work for now. Let's start up the proprietary application that was created specifically for internal testing and analysis at AtGames. To demonstrate the accuracy of flipper detection, I'll slow this video capture down to 10% of the actual footage. Remember, the camera that is recording the flipper is at a much higher frame rate. Immediately, once the flipper begins to move, the latency calculation just barely becomes visible in the upper right. As you can see, only the very first sign of flipper movement is being used in the detection and calculation. Now we have ALT fired up, the camera pointed at the flipper, and every time I press the flipper button, it writes those measurements directly to a log file. I'll go ahead and speed through the collection of 30 flipper presses so we can take a look at the results. Performing this same task manually would easily take 2 to 3 hours for taking 30 measurements. With ALT, it can be done in a matter of seconds. When I press Q on the keyboard to exit the application, it automatically handles the calculations for me. If we look closely, I can see the average latency is 55.967 milliseconds for Arkanoid, which then equates to 3 frames on a 60 FPS display, which is what the playfield is on the 4KP, and we had a total of 30 individual collection points or measurements. I hope you found this video a good overview of how to measure latency on the Legends 4KP yourself, and as well as a glimpse of our internal tool for accurately measuring latency across all tables. In part 2 of the series, we'll take a look at some of the measurements collected. If you have any questions or comments, please share them below. Thank you so much for watching, and I look forward to talking with you again very soon.